Hi, my name is Manish Gupta, and in this video, I'm going to talk about PLAVA, which is a parameter-free lava extension from images to videos for video dense captioning. Okay, so I mean, this title is okay, but let's try to understand what can PLAVA actually do. Okay, so you might remember this frame from a Sora video. So OpenAI Sora basically put out an automatically generated video. This is the frame from that video. Okay. What Pilava can do is to actually take this frame and nicely come up with a caption of this kind. So look at the richness of this caption, right? So it sort of talks about it's a dense description. It's a very detailed description of the video, including all kinds of details like motion details, attire details, background details. Even though background is blurred here, it actually calls out that there are the people in the background, but they are not the focus of the video. It also has, so it's practically a description which is not just factual, but also a description that typically a person would give if they were asked to actually come up with a caption for this kind of an image. Okay. So this is what Pilava can do. It's a good model for video understanding and also for video-based text generation. So essentially, captioning is of course a text generation task, but it can also do very good video understanding. How good can it do video understanding is actually shown on the right side. So what you see here is results for various kinds of tasks. So there are these VCG tasks for which you see these 5 metrics. There are also these video-based question answering tasks that you see results for. And also there is this MV benchmark, which is a multiple choice question answering benchmark. And you see, the metrics being plotted there. Okay? Each of these axes is, of course, a metric, right? And what you observe is that, you observe that the PLAVA model, a 34 billion model, is being compared with many other models, including GPT-4V, by the way, right? So including GPT-4V. And what you observe, so PLAVA is this red one. Of course, it is 0 here, and as you get out from the center, the metric value increases, higher the better. So therefore, the envelope as created by this red kind of a PLAVA curve is basically much larger than any other envelopes, basically saying how good Pilava is compared to any of these otherwise strong models anyway. Right? So it's basically being compared with IGVLM, GPT-4V, Video Chat 2, and Video Chat GPT as well, right? And Pilava is actually better compared to all of them. They have made their models publicly available on Hugging Face. Okay. If I look at the paper, well, the paper is not written really nicely. But anyway, the model actually works really good. Okay. So they also do a scaling study. So actually they train Pilava models of sizes 7 billion, 13 billion, and 34 billion. And clearly their 34 billion model is the best. And it is actually better compared to other baselines also. Okay. So it has better model scaling performance also. So larger models are better. Okay. So what is the Pilava architecture, right? So, in fact, what you want to do is to do video understanding. So one way of doing video understanding is to sort of extend your current image multimodal large language models, right? So there are current multimodal large language models, which basically have an image encoder. They take an image, create an image embedding, and then that image embedding is basically projected using a projector, so as to essentially get an encoding in the same dimension space as your large language model. And well, you take the question and you sort of prepend with the image embedding, and you basically just pass it to the large language model for it to generate stuff, right? So that's a typical image multimodal large language model, okay, like Video Chat GPT in that sense, right? However, the problem is that if you basically, so how can you sort of use it for videos, right? So the way you can use it for videos is that, well, you have a video, you sample multiple frames from the video, and then for each frame, you just do what a typical image multimodal large language model does, right? So essentially, you take, let's say 10 frames, equidistant frames, sampled from the video. For each of those frames, you pass it through a VIT or some such image encoder, you get an embedding, you do a multimodal projection, and then you actually have like 10 tokens, and you basically then append the answer, the question to it, and hopefully the multimodal language model will basically create a good answer. Okay. However, what they observed is that this does not work. This just does not work. It leads to low accuracy. Okay. Of course, if the video is large, this will also have scaling issues because you'll need to basically then encode crazy number of frames, right? Or you basically lose accuracy. Okay. So therefore, one of the ways of solving this problem is to downsample the video frames. So basically, you do not consume. So if you had like 1,000 frames in your video, it's not like you'll use 1,000 tokens to represent them. What you do is downsample. You could do downsampling in two forms. You could actually do spatial downsampling, and you could also do temporal downsampling. So what that basically means is that maybe you could basically take all the 1,000 frames, just pull them all together. And then, the frame may be 1,000 cross 1,000, but then you can basically do a further pooling so as to essentially reduce it down to maybe like 12 cross 12 or something like that. Okay, so that's basically what Video ChatGPT tries to do. It tries to downsample, but then loses too much of spatial information. And therefore, what Pilava folks tried to do is to come up with this kind of an architecture. It's actually very, very close to a typical image multimodal large language model architecture, but it is somewhat different. And let's talk about the two main differences, right? So rather, let me first talk about the overall architecture, and then I will talk about these two things, right? So you take the video as input, you basically sample some frames from it, pass it through VITL model, Vision Transformers large model, right? And then take those embeddings, pass it through a multimodal projector to get the projection of this size. And then you actually do adaptive pooling. So there is an adaptive pooling extra component here, which I'll talk about here, right? Which basically gives you a pooled smaller representation. And then you give it to a large language model. So you see these adaptive pooled tokens are basically here from the image. And then you, of course, concatenate your question tokens. What is this video about? And hope that the large language model is basically going to create an awesome answer. Okay. However, while training, you make this change. Of course, the adaptive pooling that you see is the new thing. And then second thing is that you take an existing image multimodal large language model and you fine tune it, but you do LoRa fine tuning. So LoRa fine tuning here is not done to make this process faster, but just to ensure that whatever the model has learned based on pre-training based on images, it does not forget that. So there's no catastrophic forgetting that happens, right? So to enable a good blend of the knowledge in the image multimodal large language model and the extra knowledge that it wants to gain from these videos and video frames, you basically use LoRa. So the pre-trained model actually retains the knowledge of knowledge of the image language model, image-based multimodal large language model, and the fine-tuning basically using LoRa. These LoRa weights basically incorporate your learning from the videos. Okay. Now this adaptive pooling, right? So they tried various forms of pooling, so spatial and temporal pooling, various factors, right? And what they did was to tune and then figure out that a particular factor helps them a lot. Okay, so they basically constructed, and we'll talk about that factor here. So they constructed, they fine-tuned Pilava on image multimodal large language models of three different sizes: 7 billion, 13 billion, and 34 billion. For the pooling layer, they uniformly sample 16 frames as input. So whatever be the size of your video, they just take 16 equidistant frames. And they set the target pooling shape to be 16 cross 12 cross 12. So that's how spatial pooling is being done. So, so no temporal pooling at all. So they basically say that, hey, I'll just take 16 frames equidistantly sampled, no temporal pooling. Spatial pooling, yes, we'll do spatial pooling where the target is set to 12 cross 12. So whatever be your resolution, basically just project it down to 12 cross 12. Okay. Now they basically do rigorous LoRa fine tuning of the existing image multimodal large language model using a whole bunch of data sets, which were also used in video chat too. Okay, this basically is about 783K instruction tuning data, conversational videos, classification kind of data sets, caption kind of data set, reasoning kind of video data sets. Of course, this is like video text kind of data sets, and then also question answering. So question answering, classification, reasoning, captioning, they basically take data sets across several tasks and in large numbers, 73K, and therefore train a robust model. Okay. So how does Pilava perform? I already showed to you how does it perform on the first slide, but it's good to compare it with the other models. So here is a video of people playing badminton in an indoor court, right? But if you ask IGVLM, what are the people doing? Well, it basically wrongly predicts that they are playing volleyball. Okay. and there are multiple nets and it has a large audience watching. There are no audience, no multiple nets, and no volleyball. Okay. But Pilava nicely basically says that they're playing badminton, and it basically also figures out the team name somehow, and so on. So they're using badminton rackets to hit shuttlecocks and so on. So basically, it more or less comes up with a very good, reasonable caption. Okay. So they experiment with a few benchmark data sets, video question answering data sets, and also experiment with the popular models. So these are the popular models that you see here. IGVLM, Llama Adapter, Video Chat GPT, all of those. And what you see here is that across all of those methods, essentially, the Pilava results are basically here at the bottom. Sorry. So the Pilava results are right there at the bottom. You do observe that compared to these baselines, the Pilava method clearly uses larger number of weights also, 34 billion weights, but compared to IGVLM Lava 34 billion, it's still doing better. It's still doing better across all those metrics. Right? So in fact, it improves over GPT-4V as well. GPT-4V has been known to be really, really good, right? So over GPT-4V also, it basically shows significant improvements, as you can see, not just for the standard video question answering data sets, but also over video chat GPT data set. So these metrics that you see here are indicative of interesting metrics like correctness of the information, detail orientation, context understanding, temporal understanding, and consistency in terms of the captions generated. Right? So on average, the model does perform really well compared to the existing baseline methods. They also do performance evaluation on MVBench, which is a multiple choice question answering method across 20 different tasks, which are mentioned here. And again, in 17 out of those 20 tasks, they basically observe that Pilava is state of the art, right? So is actually better compared to any of these existing models. In almost every task, basically, it improves over GPT-4V, except for one of them. Right? So that's basically Pilava. Okay, so in summary, in this video, I talked about Pilava, which is pooling lava. I mean, in case you were wondering what is P, right? And it incorporates two new components, adaptive pooling, which is basically hyperparameter tuning in some ways, but then done nicely, right? In the paper, they actually show what happens if you do temporal pooling, what happens if you do spatial pooling with different factors. Okay? And then they choose to not do temporal pooling at all, but do spatial pooling to downsize to 12 cross 12, right? And they also do post-optimization. They call it the post-optimization, but practically they just do LoRa, so as to retain the pre-trained knowledge of the image multimodal and large language model, and also learn good enough information from video text data sets, right? And they show that they are able to obtain state-of-the-art performance on many video question answering and video caption generation tasks. Okay, so that's it for this video. Thank you for watching. Connect with me on my LinkedIn or look at my search on my homepage. Thank you.